And so the final is right around the corner, basically, right? In like 15 days, we have the final exam. So it is not too early to start studying, right? I posted blank quizzes online over the weekend, and then this morning I also posted the relevant chapters out of the textbook that's on your My Math Lab that you can study from there, with a reminder that for the whole beginning part of the semester, we didn't use a traditional textbook approach. So it won't hurt you to look at some of the earlier chapters, but you should definitely still be looking at the PDFs that I posted under assignments that you read on your own and then answered questions from early in the semester. You're definitely responsible for that material. Okay, so just because the stuff later in the semester has been a little bit more traditional in the sense that you can open up a book and find lots of practice problems, that doesn't mean that the stuff from the beginning of the semester is unimportant. It is massively important, right? So keep that in mind while you're studying. And then if you ever have any questions about like how you can study more efficiently, right? Because I've had conversations with people who are like, I've studied for 16 hours. That seems like plenty of time to study and do well. And then maybe their performance on the test didn't match what they thought it should be. Well, to me, what that means is you're not studying efficiently, right? So we could improve your studying strategies. So I invite you to please come talk to me sooner rather than later so that we can talk about how you can improve your studying quality, right? So that's my spiel there. With that being said, I did have to modify my office hours this week, so I do not have office hours tomorrow. I don't know if you're aware, this month is Math Awareness Month, and so the math department is hosting a really cool event for like high school students in the area. But at 1:30 in the afternoon, there is like a show, basically, about math, magic, and mystery that's open to everybody, which could be fun. I guess the guy has given a TED Talk before, if you're familiar with those. That usually means that they're good speakers, right? So I imagine it'll be a lot of fun. Okay, so that means instead of having office hours on Tuesday, I'll have office hours on Thursday. Okay. All right, so let's keep going. So last time we reviewed basically a lot, and we just tried to tie together all of the pieces. I want to continue trying to develop some ideas, especially with respect to this antiderivative idea. Okay, so suppose that we have a function that is a rate of change function. Okay, then the integral from a to x of that function is an antiderivative of f. I don't think this helped last time, did it? That's terrible. Okay, so then big F of x equals e to the sine x is also an antiderivative of that rate of change function. How do we know? How would I be able to check? Take the derivative. Right, good. So if I take the derivative, so this is because big F prime of x is e to the sine x times cosine x, right? The chain rule. So, so this is also an antiderivative of f. And so what that tells us is that this thing, which is an antiderivative of f, is equal to big F of x plus some constant. So you remember last time we worked on building this image of how every antiderivative of a given rate of change function is offset by a constant. Okay? I'm using that fact here. Okay? So the integral and then big F are both antiderivatives, so they're equal to each other but offset by some constant. Okay, so that's all that this says here. Okay, so now if I think about this, well, what's going on? I could say, let's say I wanted to figure out what C was. Okay, well, the only thing I really know about or one of the things that I know about this left-hand side is that it's representing an amount of accumulation starting at A, right? So if I were to, but this whole thing is in fact a function, right? This thing right here is a function. And so if I were to plug in a value of x that is A, then the left-hand side represents the accumulation from A to A. So far, so good? Okay, but if I plug in x equals A here, then I better plug in x equals A here, because these are two functions that are equal to each other. Okay, so I can do that. Whoops, I went a little out of order, sorry. Okay, so if we think about accumulation from A to A, that's got to be 0. Okay, and then if I think about the right-hand side, well, the right-hand side, when I plug in A, equals f of A plus C. So I've got that 0 equals f of A plus C, and I can solve for C. Okay, so if I take this and sort of plug this value back in up here, then I end up with the integral from A to x of f of t dt is big F of x minus big F of A. Okay, so this is a different way of approaching sort of the thing that we were getting at last week with this resetting of your scale, right? This is resetting your scale, okay, and starting at 0 while you're looking at accumulation. Okay, so this is one way that we could figure out how to get C. Okay, now in the case of our specific function, right, that means that we're looking at the integral of A to x from A to x of cosine of t e to the sine t dt. And since big F equals e to the sine x is an antiderivative, we can use that to say, okay, so here's big F of x minus big F of A. So hopefully you had practice on this over the weekend, right? Is this feeling pretty good for people? So let's dig a little bit deeper, okay? So this is sort of the summary page, right? So what we've just established is that if we have any antiderivative, and we'll call it big F, of some rate of change function, little f, then this relationship holds, okay? So this is sort of the key relationship here, okay? Now, once again, when you look at this, this left-hand side is representing a function, right? As is the right-hand side, okay? So we can evaluate these functions at different values. And so one thing that we usually do that, right? You want to evaluate a function somewhere to find out its value. So if I wanted to figure out the total accumulation from A to B of some function where this little f is its rate of change, then I plug in B for x, right? Wherever I see an x. Okay. Now the thing that I want you to be really careful about is that, so this thing right here is what's called the fundamental theorem of calculus, okay? So when you do your homework and it says, you know, apply the fundamental theorem of calculus, this is it, okay? But I want you to be really careful because this property has enabled generations of people to do calculus without understanding calculus, okay? People love to memorize this formula and then have no idea what it means, okay? So what I'm hoping is that this entire semester we've spent trying to build up ideas and what everything means so that hopefully when you look at this, you're not just seeing a formula, okay? So here's what I'm hoping you're seeing. On the left-hand side, I see an amount of accumulation starting from A, ending at B, where the rate of change function is little f. When I look at the right-hand side, I have an accumulation function. And I've got the accumulation function at B, the accumulation function at A. So this is total accumulation at x equals B, total accumulation at x equals A. So when I take the difference, I get the total accumulation between A and B. Okay? So two different ways of representing the same thing. Okay? One using the open form and using the rate of change function, and the other using closed form and the accumulation function. Okay? So don't lose track of the meanings. All right. Now, we can verify that this property works just by checking ourselves and using graphing calculator. Did you guys bring your computers today? No? So you forgot how on Friday I said, oh, we didn't get to that part, so we'll do it on Monday instead? No? So how many people do we have enough where people can pair up with each other? Look alive. Yes or no? I need an answer. Can we proceed? Yes? Okay. So if you don't have a computer in front of you, move and find somebody who has one. All right. So I've got a list here of 3 different rate of change functions, okay? And I want to verify that looking at all of the pieces of this property will actually like fit together, okay? So what does that mean? Okay, so I've got a rate of change function. So in graphing calculator, I'm going to enter that rate of change function, okay? Now, the things that I want to check in my table are the value of this integral from 2 to 5. So do you guys remember how to type in an integral? I think it's Control-Shift-I will give you an integral, at least on a Mac. Is it different for a PC? No? Okay, great. So then we want to check this accumulation from 2 to 5. And what do I want to put in my, oh, well, I guess that's not a very good question. This is exactly what I want to type in graphing calculator, right? Remember, if the math makes sense on paper, then it makes sense in graphing calculator. So is this sensical? Can you see it? Do I need a, how do I make the, let me make the font bigger. Okay. So is this a sensical statement to type into graphing calculator? No? Why not? So I have R of t dx. That's nonsense. Notice as soon as I type in something valid, I actually get a value out, right? So once I type in something valid, graphing calculator knows what to do. It's a beautiful way to check that you're doing stuff right, okay? So here I can say, okay, so this value for this rate of change function is 0.106. What is the meaning of this number? So this is the total change of accumulation between 2 and 5. Okay. Now, what would you say is a closed form antiderivative of this thing? So when you ask yourself that question, you're really asking yourself the question, which function has a derivative of cosine of 2x? So we think maybe sine of 2x. Is that it? Okay, so if I thought that it was just sine of 2x, then I would check myself by taking the derivative, right? And when I take the derivative of sine of 2x, I get cosine of 2x times 2. So to account for that extra 2, I divide by 2. And now when I apply the chain rule, the 2's cancel. Is that okay? So let's go ahead and enter in that function. We said sine of 2x over 2. Okay. Oops. That's not where I want it. Okay. And then I want to find out the value of the change in big F when x is 5 and 2. And lo and behold, we do in fact get the same value, right? So this is a way to check your work when you're doing integration problems, right? Is you can check an open form, right? This is sort of like our trusted form. We know that this means total accumulation between 2 and 5, right? We spent weeks developing that idea, and so we can have great confidence in the fact that this really does give total accumulation between 2 and 5, okay? Here is where we can make mistakes, right? It's really easy to just be like, oh, the antiderivative or an antiderivative is sine of 2x, and just move on with your life without checking. It's so easy to do, right? And so let's say you did that and you forgot the divided by 2 right here. When you do this computation, you end up with a different number. So you have a way to check your work. Okay, use graphing calculator to your advantage. So what I want you to do right now is fill in the last 2 rows. And so hopefully if you've been following along, you'll see that this is a really easy thing to do. What do you have to do in order to fill in the last 2 rows? Do I have to close my window and start from scratch? No. All I have to do is substitute in the new rate of change functions and what I believe are our new accumulation functions, right? So give it a try. Have you been able to fill out the middle row? Yes? So what did you get for the first blank? 10.628. Okay. So then I saw a lot of people initially think that an antiderivative was e to the negative x plus 1. And then when they used that, they did not get 10.628 over here. Okay, so this is what I mean when I say graphing calculator can help you check your work, right? So once you don't get 10.628 in this column, you know that this antiderivative was wrong. Okay, so you know, and then if you go and you check yourself, you'd say, oh, okay, that's right, because the derivative of e to the negative x is negative e to the negative x. And there's no negative in front of here, right? So to account for the negative, you could think of it as dividing by -1 or multiplying by -1. It's the same thing, right? So now if I take this derivative, it's negative e to the negative x times -1, and the negatives cancel. Become positive, okay? And then the plus 1, well, the derivative of 1 is just, whoa, the derivative of 1 is just 0, right? And we want something whose derivative is x. So what has the derivative of x? 1/2 x squared. Exactly. Okay. So now when you use this as your big F of x, you do in fact get this number again. Okay. What about 3 over x plus 1? What did you get when you did the accumulation between 2 and 5? Did you get there yet? What? 5.748. What did you get for a closed form antiderivative? 3 natural log of x plus x. Okay. Could I add 5? Yes. Could I add 17? Could I subtract pi? Absolutely. So if you type this into your big F function and you happened to say plus 1700, you will still get 5.748 for this change in accumulation value. Okay? So sweet. Now there's something that I want you to attempt, which is instead of having the integral go from 2 to 5, have it go from -5 to -2 with this setup. So look from -5 to -2. What do you get? Okay, so for when you do it here, right? Or I guess -2 minus f of -5. So when you plug this in, you get an imaginary number.
I'm not sure. It says plus 0i. If there's 0i, is there actually an imaginary number?
Is it just 0i or is it like 0.0065? Okay. Well, it is an imaginary number. Why is it an imaginary number? So remember, this is the function that we're using for our accumulation. Yeah? We are absolutely outside the domain of the function. Natural log of x has domain what? What are you allowed to take the natural log of? Positive numbers. Only positive numbers. Okay? So let's make a short digression, okay, to talk about this. So if I have the function natural log of x, it is only defined for x greater than 0, right? And so its derivative, when we say the derivative of natural log of x, the rate of change of natural log of x is 1 over x, we're only talking about the 1 over x function when x is greater than 0. Okay, so the problem is that we can talk about the function 1 over x for any x that's not 0. So that means that the function 1 over x is defined for negative values of x. And so when we talk about its antiderivative, we would like to be able to talk about the antiderivative for all values of x that aren't 0, not just the positive values of x. So let me give you a visual image of what I'm talking about. Right? Because remember, we said that's the big thing. So I've got this function. Whoops. I've got this function 1 over x, right? And if I'm only looking at positive x values, then I can graph its antiderivative as the natural log of x. Now, why does this work? So if you think about up here, right, the rate of change is really big positive. So the corresponding accumulation function should have sort of like a steepness to it for the corresponding x value. So really big positive rate, really big positive slope, if you will, of the curve. And then here, the value of the rate of change is 1. And here, right, at the same x value, if you were to zoom in on the graph, the rate of change of the blue graph at x equals 1 would be about 1, right? So now we're sort of going in reverse. Instead of going from the blue to the red, you can still go from the red to the blue. We practiced that last week. Okay, but here's the problem. The graph of 1 over x isn't just in the first quadrant, right? It exists in the third quadrant as well. So if you are to try to find an antiderivative of this red rate of change graph, then you need something to the left, for negative x values, right? So far, so good? So if we reason about how would the accumulation function look corresponding to this rate of change, we'll notice that this rate of change is sort of like almost like a reflection, if you will, of what it is in the first quadrant. Okay. So then the corresponding accumulation. So here the accumulation would have some small negative rate of change, right? And then it would become a bigger and bigger negative rate of change. So in order to account for that, we can introduce an absolute value that will allow us to graph the corresponding accumulation for both positive and negative x values. Okay. So when you see a rate of change function 1 over x, its generic antiderivative is not natural log of x. You're leaving off half of the graph, or half of the function when you do that. So the actual antiderivative of 1 over x is natural log of absolute value of x plus some constant. Okay? Because if you leave off these absolute values, you only get this much of the graph over here. And you leave off this whole part of it. Okay? So that's something that tends to trip people up, is they always forget the absolute value. Okay? But this is why we have to have the absolute value. It's not something I want you to just go home and memorize, right? This is the reason for it. There's a legitimate reason why we have to have the absolute values here. Okay? Are there any questions about that before we get back to what we were doing? No? Okay. So let me just give you a quick notational note. If we have an antiderivative, so if big F is an antiderivative of little f, then we've already, right, this is the property that we established. And then this is the fundamental theorem of calculus that we all love and are not going to just memorize for memorization's sake. But here is a notational device that we often use in mathematics to talk about plugging in two different values for x and taking the difference. Okay, so saying f of b minus f of a, the way you'll see that written in textbooks is like this. So f of x, and then this bar sort of means evaluated at b, evaluated at a, and find the difference. Okay, so these notations are equivalent. Okay, this means do this. Okay, so I just wanted to point that out as well. Are there any questions about that? No? Why? I could probably find a story somewhere, but my guess is it probably has something to do with a notational device that was in physics first. But I'd have to look it up. I don't know idea. Okay. All right. So from integration unit. So this actually gives you an equation to look at from our example from last Friday, where we were talking about the accumulation of elevation as you drive. I talked about driving away from the coastline, but this is going to be in feet of elevation per mile of highway for a stretch of Colorado highway going east of the Utah border. I really wish I had looked at a map. I don't know where these states are, but is that legit? Is Colorado east of Utah? No? Yes. Okay, cool. I mean, I assume it's true, but that's actually something that's characterized as a habit of mathematical thinking, is fact-checking. right? That's not actually something that the people, like an average person in the population does. You tell them something and they sort of take it for granted. It's a very terrible thing. Don't take things for granted. Fact check. Okay. I have a fun story about that. Can I tell you a fun story? So there's a clipping in a sort of like a scientific journal for kids that said that an aphid will hatch 21 followed by 105 zeros. So that many eggs in a 10-month period. Wow, right? Okay, so I saw that and I was like, that's weird. First of all, do I believe it? So, like, second graders had counted the zeros, right? And they had, like, gone online and researched that, like, 10 to the 10 is a Google, right? And so, or 10 to the 100, sorry, is a Google. And then, like, they had read something about a Googleplex. And so they were like, so do you call this thing a Googleplex? Because there's more than 100 zeros. And so I was like, well, this is interesting. So I looked at it and I was like, okay, well, there's actually not 105 zeros. There's actually 108 zeros. So this number is even bigger, okay? But then if you think about that number, is anybody really uncomfortable with that number yet? So let's think about that for a second. If each egg was 1/1,000,000th of a gram, you would still have 102 zeros. So 102 zeros after the 21, and that number of grams would be the total amount of weight of the eggs laid by this aphid. Okay? So then if you wanted that in kilograms, chop off 3 more zeros. So, okay, now we're down to 99 zeros after 21 kilograms of weight of eggs. This is excessive. Okay, so any physics majors in here? No physics majors? Anybody who just likes to geek out and knows the number of atoms in the known universe? It's not infinite. So the estimated value of the number of atoms in the known universe is on the order of 10 to the 80. So if an aphid was to lay 21 times 10 to the 109 eggs in 10 months, that aphid would have to eat the entire universe in atoms like 100 times over in order to pass that many atoms through its body. This is what I mean when I say fact-checking and critical thinking. These are powerful things that you should hopefully take away from this class. Okay. Don't believe everything you read. All right. So the rate of change of elevation. Okay, so we have this formula for the rate of change of elevation of highway, right? And so if I wanted to graph the change in the highway's elevation, starting from the elevation at the border as a function of the number of miles, I could use this rate of change. And how would I go about actually trying to graph? How could I strategize to graph the accumulation, right? Or sorry, the change in the highway's elevation as a function of the number of miles? Do you have a way of thinking about that? I'm going to highlight some words. So how can we think about change in elevation relative to having a rate of change of elevation? Joseph?
Well, it's also the rate of change in feet. And once in miles, see
Oh, no. It doesn't want the change in elevation as a number of miles. It wants the change in elevation as a function of the number of miles from the border. And its rate of change is the rate of change in feet per mile of highway. So in both cases, so like if I were to graph the rate of change function, I would have x in number of miles, and then my vertical axis would be in feet per mile, right? And then if I go to actually graph the change in elevation, I'm going to have, again, x is the number of miles, right? And then I'll have feet in elevation on my vertical axis, okay? But how would I compute changes in elevation if I have the rate of change in elevation? Arian? Write the accumulation in open form. I sure could. So that would look like the integral from yeah, right? So here is my highway's elevation function, accumulation of elevation, right? Okay. Now, so I could literally just type this into graphing calculator and it'll produce a graph. Okay, that's the easy way. Now, just since we're already starting to think about the final exam though, how would you think about this in a more basic way? Like if you didn't have a graphing program. I hear mumbles. You got to be more brave. Okay, so you could find the closed form antiderivative. Okay. What's a way that uses the fundamental concept that drove the first 8 weeks of the semester? How did we get accumulation from rate of change? You get little bits of accumulation from a rate times a little bit of change in whatever your input is, right? So you could also think about this, you know, if you really had, and I think this was on a quiz recently, maybe, right? Where if I give you rates, then you could compute accumulation by taking those rates and little bits of changes in x and computing the corresponding changes in y. And you could roughly sketch an accumulation function that way, okay? So let's not do that, okay? Let's use the fact that we have a graphing calculator though. And so here we have our highway's elevation, right, as a function of the number of miles from the border. And so if I wanted to compute the accumulated change in elevation from mile 2 to mile 5, I could straight up use this, right? How would I represent that change? So this is the difference between computing and representing in my class, right? It's a big difference. How do you represent the change in elevation from mile 2 to mile 5? Okay. How would you show that on the graph? So this is a really nice symbolic representation to represent the exact change in accumulated elevation from mile 2 to mile 5. This is beautiful. How would I show it on this graph? So if I come, so here and here, am I looking at these points? Do these points tell me the change? The change in the y value here, right? If I were to draw a horizontal line here. So this is the change in elevation, right, that is represented by this integral. Okay, so this right here would be a representation of this change. Okay, so make sure you're drawing these connections when you're studying, right? Don't just plug and chug and be done with it. Okay. So here's exactly what you told me, though. I could represent it symbolically, represent the accumulated change in elevation symbolically using this formula, and do some handiwork to actually find an antiderivative of this given rate of change. Use my fancy schmancy mathematical notation to say that I'm going to evaluate that antiderivative between 2 and 5. So this fancy notation, all it means is plug in 5, plug in 2, take the difference. Okay? And that'll give you some numerical value. Okay? I probably shouldn't have told you that story, so I could talk about more how I could, how do we actually find this antiderivative? But let me just sort of give you a word of warning that there is a lot of chain rule activity, right? The catch is you're doing it in reverse. So anytime you see an integral where the rate of change function inside the integral has some sort of product involved, don't think product rule, think chain rule. Because remember, the outcome of a product rule is the sum of two things being multiplied. And half the time when I give you something, it's not the sum of two things being multiplied, it's just one thing that's a product of two things, right? So it's not the outcome of a product rule type derivative, right? It's the outcome of a chain rule derivative, right? Because remember, when you take the derivative of something using the chain rule, the outcome is the outer function with the inner, right? The derivative of the outer with the inner plugged in times the derivative of the inner. So the outcome of the chain rule is a product. So if you're trying to find an antiderivative of a product, chances are it was a chain rule type thing to start with. Does that make sense? So kind of my word of warning is that there is no such thing as a product rule for integration. Okay? Well, there is, but it doesn't look the way you want it to look, and it's something for Calc 2. Okay? So you can deal with that next semester. Okay? But for our class, there's no such thing as a product rule for integration, so don't go there. Shoot. Okay, I'm out of time, so I'll stop. And we'll keep practicing these things. My goal is to finish all of the material by the end of this week. So next week, we will be reviewing for the exam. That means you guys have to start studying, right? Because reviewing for the exam is only as productive as the work you put into it, okay? So keep that in mind. Start preparing questions, things that you want to ask about.